In the summer of 2022, less than a month after the James Webb Space Telescope, or JWST, began releasing its very first scientific images, astronomers noticed something that instantly sparked both excitement and confusion across the astrophysics community. Tiny, unusually bright red dots scattered throughout JWST's deep field photographs. Because the telescope offers unprecedented sensitivity, revealing structures and light sources far too faint for earlier observatories, these little red dots appeared with remarkable clarity. What made the discovery even more surprising was the sheer number of them. It wasn't just one odd object here or there. JWST had unveiled what seemed to be an entirely new population of celestial bodies, previously invisible to instruments like the Hubble Space Telescope. This invisibility made sense to experts familiar with telescope capabilities. When astronomers describe an object as very red, they are referring not to its color in the everyday sense, but to the fact that it emits most of its light at longer wavelengths. These wavelengths fall in the mid-infrared region, stretching beyond 10 millionths of a meter, far outside the range Hubble was designed to observe. JWST, with its infrared-optimized instruments, was built precisely for this kind of detection, meaning these strange objects had been hiding in plain sight for decades, waiting for the right technology to reveal them. As astronomers began to collect additional data, one fact quickly became clear. These objects were astonishingly far from Earth. Even the nearest among them were located at distances so immense that their light had taken around 12 billion years to reach our telescopes. Because observing the cosmos is essentially a form of time travel, astronomers realized they were looking at these mysterious red sources as they existed nearly 2 billion years after the Big Bang, during a period when the universe was still very young and rapidly evolving. It was at this point that the situation became much more complex. Interpreting astronomical observations is impossible without reliable physical models. When scientists identify something as a star, galaxy, nebula, or black hole, they do so only after comparing its observed properties, brightness, spectrum, shape, energy output, to models built from decades of theoretical understanding and previous observations. A star, for example, is understood to be a massive sphere of hot plasma, bound by gravity and powered by nuclear fusion at its core. If an object's appearance and spectrum match those expectations, astronomers can confidently classify it. But the newly discovered little red dots did not fit into any familiar category. Their spectral signatures, brightness levels, and compact sizes did not align with the behavior of typical stars, standard galaxies, or known types of black hole activity. Because the standard models offered no obvious explanation, astronomers were forced to consider more exotic possibilities. One of the first major interpretations proposed was nothing short of astonishing. Perhaps these red dots were extremely dense, dust-enshrouded galaxies packed with unprecedented numbers of stars. To illustrate this, consider our local neighborhood within the Milky Way. If you place our solar system inside a cube 1 light year on each side, that cube would contain only one star, the Sun. The rest of the space is mostly empty. By contrast, in the proposed ultra-dense galaxies designed to explain the little red dots, a cube of that same size might contain several 100,000 stars, all crammed together in a hyper-compact environment. The only region in the Milky Way that even begins to resemble such density is the galactic nucleus. But even that environment contains about 1,000th of the stellar mass required by these extreme interpretations. To suggest that such galaxies existed less than 1 billion years after the Big Bang raised enormous theoretical problems. How could so many stars form so quickly? What mechanisms could drive such explosive early growth? As one researcher, Bingji Wang of Penn State University, put it, the night sky of such a galaxy would be dazzlingly bright. If the interpretation were true, it would imply that the early universe hosted star formation processes far beyond anything previously observed or even predicted. However, not everyone agreed with this explanation. The community soon divided into 2 major camps. One group supported the idea of extraordinarily star-rich galaxies heavily obscured by thick clouds of dust, while the opposing group argued that the little red dots were not galaxies at all, but instead were active galactic nuclei, regions surrounding supermassive black holes that emit enormous amounts of energy as gas spirals inward. These black hole systems are known to glow brightly at infrared wavelengths, especially when heavily veiled in dust. But this interpretation faced serious complications. The spectra of the little red dots differed noticeably from the spectra of dust-reddened active galactic nuclei previously catalogued. Moreover, to explain their brightness using black holes alone would require the black holes to be astonishingly massive, far larger than expected so early in cosmic history, and would imply a surprisingly large number of such objects existed. That many supermassive black holes forming so soon after the Big Bang challenged fundamental theories of black hole growth and galaxy formation. Despite their differences, both camps agreed on at least one thing: more data was needed. The initial JWST observations had provided images, but images alone cannot reveal the detailed physical nature of an object. To distinguish between competing interpretations, astronomers would require spectra, measurements of how much light the object emits at different wavelengths, to expose its chemical composition, temperature, age, and internal structure. Because observing time on JWST is extremely limited and highly competitive, scientists across the globe rushed to submit proposals focusing on these puzzling red objects. Among the selected programs was Ruby's project, short for Red Unknowns, Bright Infrared Extragalactic Survey, led by Anna de Graaf at the Max Planck Institute for Astronomy. Ruby's was granted nearly 60 hours of JWST time between January and December of 2024, an extraordinarily large allocation that allowed the team to collect spectra from 4,500 distant galaxies, one of the biggest spectroscopic datasets obtained by the telescope. Within this dataset, the team identified 35 of the little red dots. Most had already been seen in earlier public JWST images, but a few new, previously unnoticed ones appeared as well, and these turned out to be the most extreme examples yet. Among them, one object discovered in July 2024 stood out dramatically. The researchers nicknamed it the Cliff, not only for its distinctive spectral shape, but also because it represented an extreme case within this mysterious population. The cliff lies at such an enormous distance that its light has been traveling for nearly 11.9 billion years before reaching Earth, corresponding to a cosmological redshift of z equals 3.55. What captivated astronomers most was the object spectrum. Its defining feature is a dramatic, cliff-like rise in brightness at wavelengths that would originally have been part of the ultraviolet portion of the electromagnetic spectrum. Light slightly shorter than visible violet. But because the universe has expanded over nearly 12 billion years, stretching the wavelengths of distant light in the process, that ultraviolet signature has shifted into the near-infrared region by the time JWST detects it. This steep increase in brightness is known as a Balmer break, a feature created when the atmospheres of stars absorb certain wavelengths of light. Balmer breaks are commonly observed in ordinary galaxies, particularly those that have stopped forming new stars. However, the Balmer break seen in the cliff is far more intense than anything recorded in typical galaxies. Its extreme steepness suggests an unusual combination of factors, perhaps an aging stellar population, a unique structural configuration, or even a form of energetic activity not yet fully understood. Because the cliff is so extreme, scientists believe it may hold the key to understanding all the other little red dots. If researchers can explain what physical processes create a spectrum like the cliffs, they may finally unravel whether these objects are ultra-dense star factories, heavily obscured black hole systems, or something else entirely, something that could force astronomers to rethink early cosmic history. The discovery underscores the transformative power of JWST. Instruments capable of observing the universe at unprecedented depth and sensitivity inevitably uncover phenomena that challenge established theories, push scientific imagination to new limits, and remind humanity that the cosmos still holds countless mysteries waiting to be understood.